Okay, so in this video I'm going to show you how to implement a queue data structure, and I'm going to do it in Python, but I'm going to do it the way that the A-level exam papers tend to do it. They'll do it in their pseudocode, but since I can't write and run that, I thought I'd do it in Python just to show you how it's done. So a queue is essentially a list, but it has restricted access methods. It has an enqueue method, where we add things to the end of the queue. It has a dequeue method where it takes items off the front of the queue. So you can think of a line in, I don't know, McDonald's or something like that. Once you've got your food, you leave the front of the queue, but you join the back of the queue. And it has two other methods that at least AQA want you to implement, which are full and empty, which return true or false depending on whether or not the queue is full or empty. Now, let's have a look at these bits of code and the queues that result. So we enqueue 34, 28, 53, 11 and 82, and we end up with the queue in this state. We maintain two integers here, which are indices into this fixed length array, or I'm going to do it as a list in Python. And instead of, if you were doing this dynamically, that's to say with a data structure that uses references to objects, these values would be references to a node at the front of the list and a node at the back of the list. But when you do it statically like this, that's to say with contiguous memory addresses, you're going to use indices to mark where the front and the back are, and you'll need that information in order to put things in the right place and take them off at the right place when you enqueue and you dequeue. Now, an important thing to realize is that when you dequeue something, that means 34 will leave the list, and we'll have this sort of funny list hanging around in the middle of the memory space that we have for our list. That in fact is the normal implementation of a queue. I've seen teachers on various forums and so on arguing that once you dequeue 34 here, you should move 28 and move 53 and move 11 and move 82, but that would change the dequeue operation from being a constant time operation to a linear time operation. That's to say, instead of being order 1, just removing this, it becomes order n, because for every item you have in the list, you then have to perform an operation to move it. That does make life a bit easier insofar as you don't get this problem with the data moving through the list as you do with the efficient implementation, but it really isn't the way that queues are implemented. So if you end up implementing a queue as a static data structure like this with these contiguous slots of memory space, you always have this problem of the data migrating through the list, and then when it gets to the back, it has to wrap around. So in this state here, the front of the queue is in fact here, and the back of the queue is there. And so you end up with this circular structure. So what you're looking at here is not only a queue, but a circular queue. Circular queues are used very often in things like keyboard buffers. If you look at Wikipedia for a circular queue or circular buffer, there's quite a nice description of how keyboard buffers work. Okay, so let's look at how I would do this in Python. I'm going to start off with my queue. I need some way of creating my queue. It's going to have a max number of items, because otherwise it doesn't make sense to have a full method. What else do I need? Enqueue, which is going to take some data item. Dequeue, which won't. And I want full, and I want empty. So that's the basic structure of the methods that I'm going to have in my queue. I can add a couple of things at this point quite easily. I'm going to, instead of calculating whether or not the number of elements in the queue, you can do that by sort of subtracting the value of the head of the queue from the tail of the queue and stuff like that to work out how many data items are in there. I'm just going to maintain an integer to do it for me because I think it's easier. It must therefore be true that I'm full if my size is equal to my max size. So that means I'm going to have to remember what my max size is. Let's just call it max size. So self dot max size equals max size. So just to be clear, when I create my queue, I'm going to do something like this: queue equals queue, and if I put an integer in there, I'm going to get a queue of that size with 5 slots. And the number that I pass in will temporarily be stored in this parameter variable max size here, and then I'll take max size and I will assign it to an instance variable max size, which I can then use to calculate whether I'm full or not. So this, I think, is already sufficient for my full method, and this one self.size is equal to 0, and that's sufficient for my empty method. I know already that I can, when I enqueue something, I want to make sure that I check to see if I'm not full, because I can't enqueue something if I'm already full. So if not self.full, then I'm going to go ahead and do something else. In this case, I'm just going to print a little message which says queue is full. I think if you were implementing a queue in a proper production system, you would raise some sort of exception here. You wouldn't just print a message. But in this simple implementation, I'm going to do this. To be honest, if you were implementing a queue in a production system, in a proper professional piece of software, you wouldn't do this at all. You would use a built-in data structure. There's a data structure called a deq in the collections library, which is probably the right implementation for a queue. A deq actually is a double-ended queue, but you can just restrict yourself to some of the methods of it so that it only implements enqueue and dequeue. Let's have a look at dequeue. If not self.empty, I want to go ahead and do what I do. Otherwise, I'm going to print queue is empty. Okay, so this much I know so far, and I now just need to work out what enqueuing something involves. Well, first of all, I need to be sure that I keep the index of the front of my queue. I'm going to call it head. It's quite common to do that. And so self.head is 0. Self.tail also is going to be 0. So that's the front of the queue and the back of the queue and the size of the queue are all going to be 0. And the last thing I need to do is to have somewhere to actually store my my items, and that's going to end up being not just an empty list, but I'm going to make it a fixed size list in which every item is none, and the size of that list is going to be self.max size. So that starts me off with a queue of, if I were to use this constructor call here, it would give me a queue object with 5 nones in it, and then I can go ahead and start adding things. So when I enqueue, I'm going to put something where the tail is, and then I'm going to increment the position of the tail. So in fact, my tail is going to point to the next blank item after the end of the queue, and that's how I've decided I'm going to use it. So self.items, and the item I want is the position of self.tail, and that's going to become the item. And then I can say self.tail plus equals 1. So I've acknowledged the fact that I've added an item to my tail here. I think I also want to do self.size plus equals 1, and I have one other thing to check here, because if I've got to the end here, if I'm enqueuing something here, I want the next index to wrap around all the way to here. So if after I've added something here and incremented the tail is equal to the max size of the queue, in this case it would be 8, because there are 8 items here, 0 based. If my tail is the max size, then I want the tail to be 0. And that's what I'm going to do here. So I just do a quick check. If self.tail equals self.max size, then self.tail equals 0, and that's sufficient to wrap me round. Okay, and I think that's okay for the enqueue method. Dequeue, here I've got to take the item, take the head, and I've got to increment the head now of the queue. So I want to, that's the way in which I'm going to remove the item at the head of the queue. And the way that I then do that is, it's just my family sending me messages all the time. I need to remember what's at the head of the queue. Let me just pause this. Right, hopefully that'll solve that. I'm going to hold on to the item that's at the head of the queue like this. Then I'm going to move the head of the queue forward one, and all I need to do at this point is check whether or not my head has now run off the end of the queue. So if I'm in this funny position here, where I'm dequeuing from here, what I'm doing is I increment the pointer to the head, and in doing so, this is no longer at the front of the queue. This is, and if I increment so that I've come off the front of the the back of the queue here, the back of the data structure, I need the head to wrap around to 0 again. So let's just check here. So if self.head is equal to self.max size, then I want self.head to equal 0. Is there anything else I need to do? Yes, I need to reduce my size here. Let's do it. Self.size minus equals 1. And I think that should be okay. If I do this, what will happen is that after I dequeue an object by incrementing my head pointer by 1, this data item will still stay there, and that looks will look a bit weird when we look at the way that the data structure appears when we run this. So what I'll quickly do is just at this point I'll just say self.head equals none. This isn't necessary at all, but it will make it clearer what's going on when we run the code. Okay, I think at this point I've got to return my item. because the dequeue method does that. And just to be explicit, I'm going to return none here. I don't do that in the enqueue method because the enqueue method shouldn't return anything anyway. Let's see how this works. Okay, so no mistakes in it. Queue equals a queue of length 5. And I should have a queue object here. It's all nuns at the moment. The head is 0, the size and the tail are 0, and the max size is 5. So that's as expected. Queue.enqueue, I'll enqueue the number 1. And that's what my queue looks like. That's as expected. Let's put number 2 in and a number 3 in. And I'll try now dequeuing. And I've got an error. Okay, so self.head plus equals 1, unsupported operator types for plus equals none type. Right, well, that's going on there. Head equals 0. Where is this? Self.head equals none. Yeah, I can't do that. Yeah, self.items at self.head should be turned to none. So that's just a small error there. Let's run this again. So hopefully I should be able to create my queue in Q1, in Q2, and in Q3. So we're back where we were, and then I'll try dequeuing. And now we've got the front of the item. So 1 was removed. Q.dequeue removed 1 and returned it. Because I've taken the time to set this to none, now it's clear what the structure of our queue is. Let's just keep enqueuing stuff now to see what happens. Let's put 4 in, and now let's put 5 in. And now the test will be what happens when I put 6 in. 6 should go here to this. It's still the back of the queue. It's not the front of the queue, even though it looks like it is. And I know that because of where my indexes for head and tail are. The head is telling me that item 1 is the front of the queue, and the tail is also here because this is supposed to be the space after the back of the queue. If I try to enqueue something else here, I should get my error saying the queue is full. And if I dequeue at this point, I should get the 2 coming off. Yeah, so the 2 comes off there. So this seems to be working. Let's keep dequeuing. And I've now got a queue again where now 6 is at the front because everyone else has left the queue. I'll dequeue once more. And then here I should get an error saying that my queue is empty. Okay, so that's a basic implementation of a queue using a fixed length list. So essentially a static implementation of a queue, which is also, as it always will be if you do it efficiently, a circular queue.